So today we will discuss about the our subject name is integrated circuits and its applications. So in this we will discuss about the op-amp. What is the op-amp? Op-amp is nothing but operational amplifiers. So in the operational amplifier, so we will discuss its characteristics, its applications, different things. So operational amplifier is a direct coupled high gain amplifier. This is the direct coupled. This is the first is a it is a direct coupled high gain amplifier. Usually this consists of a one or more differential amplifier. Generally it consists of the one or more differential. This is a high gain coupled amplifier. This is the high gain coupled amplifier. You can differential amplifiers and followed by level transistors. Operational amplifier generally available in single ICs, packs, and the operational amplifier also versatile. It can be performed. There are so many types of applications used for DC amplify. The quality of this, it can be used for DC amplification and AC amplification. Both the operational amplifiers can be used. Means it can amplify the DC and it can amplify also AC. There are different type of mathematical functions can be performed, just additions, subtractions, multiplications, integrations. All these applications can be performed by operational amplifiers. Thus, name of operational amplifier stems from the original use of these mathematical operations and abbreviate it to op-amps with addition of suitable external feedback component. In the modern day, the op-amp can be used to a variety of applications such as the AC/DC signal amplifications, addition, subtraction, AC/DC signal amplifications, active filter, passive filters, comparator, regulator. All the things can be implemented using the operational amplifiers. This is the block and this is the diagram of this operational amplifiers consist of one. This is the two inputs. This one is inverting inputs, second is non-inverting inputs. This is and one output terminals, and this is the here up to one power supply is also here. This is the VCC saturation positive, or next is a VC saturation negative. VC saturation, VCC minus, VC saturation negative. Generally, so this is the and this is a block diagram of operational amplifier. This is non-inverting input terminals, and at the input or this is a dual input balanced output. There are four variety of inputs are available. First, dual input and balanced output at non-inverting inverting terminal. This is the dual input. In dual input, this is the and balanced non-inverting. Second is a dual input and balance. Balance means both inputs are equals, and this second is a unbalanced output. And third is a level shifter, then intermediate stage, level shifting stage, the emitter followers that put the constant current load, then the output stage, comprehensively symmetrical outputs are there. So some characteristics we will discuss about the ideal op-amps. Actually this is practically not possible, but theoretically it is possible. So then we will discuss about first ideal op-amps, and second we will discuss about the practical op-amps. And ideal op-amps is a devices which hold different characteristics. Yes, it has a high infinite voltage gain. It is the infinite voltage gain must be infinite. Voltage gain must be, but actually infinite voltage is not possible, but it's practically its gain must be very very high. So ideally we can create its gain approximately infinite. It has zero offset voltage. Then that is a zero offset output voltage obtained using when both op-amp have even zero differential input stage. Means what is the zero offset means? That means if we apply, this is the op-amps, in this op amp, if we apply the two inputs, input 1 and input 2, two inputs, V1 input and suppose that V inputs, and that means zero offset means that both input, that is a zero output when we obtain even for zero differential inputs, means we are providing both input must be V1 approximately V2, V1 approximately equal to V2 approximately equal to 0, then output must be 0. That time is called it, which outputs we will get, that's called the zero differential output voltages. So it should be, ideally it should be zero differential, zero offset output voltage, but practically it is not possible because of their op amps internal designs, because in op amp there are so many types of transistors they use. Because of these transistors it creates some offset voltage that cannot be zero ideally, so practically, but ideally it may be zero. Second things we will discuss the what the bandwidth. It has infinite bandwidth. This second term, it should be infinite bandwidth. It should be, bandwidth must be infinite ideally, practically. It has zero output impedance. Op amp must be zero, means output voltage must, or resistance must be equal to 0, but it is not possible practically, but ideally it should be 0. Second things we will discuss about the R output equal to 0. It has input impedance must be infinite. Output must be 0 for any ideal op amps. B generally considers input infinite must be, input resistance must be infinite, so that there is no current flow through that devices. So in that condition the loading effect will not be occurs. That's why we try to maximize the input resistance. In case of ideal op amp it must be infinite. So this was the ideal characteristics of op amps. Right now we will discuss about the some practical characteristics, that differ from the ideal characteristics of the op amps. So first we will have to discuss about the open loop gain. This open loop gain of practical amplifier, it must be around the 7,000, 7 to 8,000, 10,000 approximately. But it's, in case of ideal it was infinite, but practically it should be approximately 10,000, 7 to 10,000, ideally 7 to 10,000. The practical op amp has non-zero offset voltage. Initially we have discussed ideal op amps, the offset must be 0, offset voltage must be 0, that's the output, zero output obtains in op amp even for in differential input is 0. Means the here the output zero offset voltage should not be 0, it must be some value when we are applying this zero differential input voltage to the op amp of both terminals. Next, bandwidth. The bandwidth of practical op amps is very small because gain should be very high, because we know the gain into bandwidth for any operational amplifier is constant. So if the gain range is approximately 7,000 to 10,000, so that time the bandwidth of the practical amplifier should be very less. This can be increased by desired value applying the adequate negative feedback. Whenever we apply the negative feedback any op amps, so it reduces the gain. We have already discussed in previous classes. It reduces the gain of the amplifiers. The beauty of the negative amplifier, when we apply the negative feedback in op-amps, it reduces the gain of amplifier. When the gain of amplifier is reduced, that time the bandwidth will increase, because the product of gain into bandwidth, any amplifiers, that must be constant. If the gain is reducing, that time bandwidth will be increased. So this is the negative feedback amplifier diagram. Output impedance in order to 100 ohms. In ideally it was the 0, but it is the 0 is not possible in practical cases. Its range must be very so small. Let's say approximately we can say 100 ohms range. That can be minimized by applying the negative feedback. Even second beauty of negative feedback is it reduces the output impedance and it increase the input impedance. That's why we use the negative feedback. Second things, the input impedance in order to mega ohms. In ideal op-amp it was infinite, but that was not possible practically. So that time it must be approximately 1 to 10 mega ohm range in practically. So this was the some characteristics in practical operational amplifiers and ideal operational amplifiers. Second, input and output characteristics of practical amplifier. The maximum output of op-amp is limited by DC power supply to op-amp. So the maximum output of op-amps is limited by the DC, because whatever DC supply, we have already discussed about the VC saturation, that's the supply. So it's limits by the DC. What if we are applying the 10 volt VC supply, even we are providing the 100 volts input, that time this output will not be exceed the 10. Even we are providing the 100 volt input, but VC saturation, that is supply voltage provided to op-amps is 10 ohm. So that time output will not exceed the only 10 ohm. So this is the limited by the DC power supply or op-amp. At the most output voltage limited by VCC plus VC saturation and VCC minus saturation. Even input is more than VC saturations, positive and negative, but output will be less than VCC positive and negative saturations. Similar output current from the op-amp is also limited by these saturation voltages. Below so we can see the one example of the op-amp operational amplifier. The gain, if the gain range is 1000, even gain is approximately 12,800, something like that. And power supply equal to, suppose that power supply 9 volt 10, that we can assume this is a 9 volt here. When input voltage exceed the plus minus 10 microvolt, then output start to use non-linear characteristics or plus minus. So this is the graph we can see here. This is the output voltage here, and this is the input. At data input is up to goes up to here increasing, then output can be increased. It's reach the 9 voltage. 9 voltage is nothing but VCC supply, which is that is in a power supply. This is saturation voltages. VCC saturation, that's power. After the input increasing VCC, then output must be constant at 9 voltage, and this region is called its saturation region. From here said op-amp output is saturated. So this is that graph how the op-amp is working when we are applying the any inputs. This input is increasing up to minus VCC saturation. This is the VC saturation negative. After this VC saturations, output is increased. and at this position it remain constant even we are applying the more and more inputs. So we will see the difference between the ideal op-amps and practical op-amps. First is the voltage gain. Voltage gain must be infinite. हाँ सर, हाँ सर, अभी थोड़ा सा 20 मिनट बाद क्लास ले रहे थे तो आते हैं 20 मिनट बाद. ठीक है. So voltage gain is for in case of ideal op-amp infinite, and practical in case of practical op-amp it must be high. Input resistance infinite in ideal cases, practical it must be high. Output resistance in ideal op-amp is 0, but practical it will be low. Bandwidth in case of ideal op-amp infinite, but practical it must be high. CMR in case of ideal infinite and practical high. Slew rate in case of ideal op-amp is infinite, in case of practical is very high. Some characteristics we will discuss about the op-amps. So first we will discuss about the DC characteristics, which is the direct current. So DC characteristics include करता input bias current, input offset current and input offset voltage. First is input bias current. This is the input bias current. Next is input offset voltage, then input offset current and offset voltage. 4 characteristics we will discuss, and thermal drift one by one. Next is the AC characteristics. In AC characteristics we will discuss about the frequency response, slew rate. These are the AC characteristics. So what are the DC characteristics? In ideal op-amp it draw no current from the sources, because we have ideally assumed that its impedance is infinite. In case of input impedance is infinite, so there is no current will flow from the op-amp's inputs. Its response is also independent from the temperatures. However, real op-amp does not work in this way. The current is taking from the source into op-amps. So, and also input respond to differently in current and voltage due to this mismatch of the transistors. A real op-amp also shift the operation with temperatures, means its output is also changes as temperature changes, because temperature changes, because this op-amp is designed using a different type of transistors. So in transistors input offset voltage changes, internal base emitter voltage also changes, all these parameter changes. So that's why output of the op-amp will also changes as temperature changes. So these non-ideal DC characteristics that add the error component to the DC output voltages. First, so what that output are include first input bias currents IB. First, this name is input bias current. This also DC characteristics input IB. This input bias current. Input offset current. This is the also input offset current. Then input offset voltage and thermal drift. So what are the input bias currents? We will see about the input bias current. It is defined as the average value of base current entering into the input terminals of op-amp during the input bias current. Suppose that this is the op-amp. We will draw the one diagram here. Suppose that this is the op-amp. This is the IB1, current IB1 is here, and second here is IB2 is here. Then this is the output. Input currents during the op-amps. So we can, what is the offset voltage? This average current B1 equal to IB1 plus IB2. So we can take the average of current which is flowing through the terminal 1 and terminal 2 is nothing but inverting and non-inverting terminals. that currents, we will take the average of that current. This is called it input bias current. Op-amp circuit is a differential amplifiers which may be made of the BJT, FET. Either in case of input transistor, it may be based on into linear or saturation. The current is drawn from the input terminals. However, practically, input terminal do conduct a small current DC to the bias transistor. So the base current entering into inverting terminal and non-inverting terminals. Suppose that we have assumes IB negative is inverting terminals and IB positive is a non-inverting terminals. Then we can take the average of both. So some values, the base bias current, input bias current for the, in case of BJT it must be 500 milliamperes. In case of FET it must be very less. It must be approximately 50 picofarad. So in case of BJT, input bias current is very less. When we are design the op-amp using the FET, so bias current must be 50 picofarad. In case of BJT, it is op-amp design using the BJT, its bias current approximately 500 milliampere. By introducing the compensator resistance in non-inverting terminals, we can reduce the input bias current. So second, how will reduce this current? So what we will have to do? Suppose that this is the one op-amp circuit resist. This is the positive. This is the negative. This is the I1. And this is the I2. IB1. IB positive. Suppose this is the IB negative, and here is IB positive. And resistance is suppose that here R1. And suppose that here this is the negative feedback. Suppose that this is the feedback resistance RF. Here feedback applied RF. This is the feedback. And so what is the input? What is the compensation resistance? R compensation. This is the R. Here if this is the R compensated resistance, compensated, then equal to R1 parallel RF. So this value equal to, we can write R compensated equal to R compensated resistance is nothing but RF parallel. This is the R1 input resistance parallel to the RF feedback resistance. If this value of resistance be apply here, non-inverting terminals here, so then it reduce the input terminal input bias currents. So this is one method. Second, we will discuss about the input offset current. Previously we have discussed the input bias currents. So what is the input offset current? The bias current compensated will work efficiently if both bias current I1 and IB2 are equal. The input transistor cannot be made identical, hence there will be a difference in bias current. So this difference is called it input offset current, and this can be written by this. Whenever this operational amplifier, this is the if the base offset IB negative here, the negative here, and this is the IB positive here, we can say that if these I1 and IB2 are both are equal, then there is no offset current is there. If this value is not equal, then it creates the input offset current. So what is the input offset current? Is the difference between the current flow from the non-inverting terminal minus inverting terminal current. In this way we can decide the value of input offset current. In case of BJT, it must be 200 nanoamperes. In case of FET, yeah, or MOSFET, it must be 10 picofarad. This effect also can be caused minimized by the having a feedback resistor value to be small. If the be provided by very small feedback resistors in op-amps, this value can be minimized. Suppose that if then we will discuss about the input offset voltage. It was the input offset current, because input offset current exists, because of this current input offset voltage will also be exist. In spite of the use of above expression, we can use different techniques. It is found that the output voltage may still not be zero with input voltage is zero. Even we are applying the both terminal input voltage, after that output will not be zero. That voltage, so this voltage due to unwired or unbalance of inside the op-amp transistor is used. So even we have applied the both inverting and non-inverting terminal of input zero input voltage. After that, it create the some output voltage value. That value is called it input offset voltage. So we can see by the diagram. Suppose that this is the op-amp. This is the we have applied voltage V1 negative here, positive here, and second this is the V2 negative positive here. This is the V output voltage. Even we grounded both inverting and non-inverting terminal. After that, this is the R2 or this is the R1, suppose that R1. So even we have applied it the both terminal into ground, after it create the some value of output voltages, that is called it input offset voltage. So what this value? This value is equal to, this is the R1, this is the input resistance divided by a R1 plus RF nothing but feedback value resistance into input offset voltages. That is called it input offset voltages. So what is the value of input offset voltages? So this is the, practically we can say like that, input offset voltage VOS. This VOS is nothing but this is the difference between the V1 minus V2 is VOS. This is the VOS. So this is the V1 equal to, this is the VOS. Next and last DC characteristics of transistor is a thermal drift. The bias current, offset current and offset voltages with changes with the temperatures. All these value we have discussed about the input offset voltage, input offset current and input offset. All these value will changes according to temperatures of the surrounding changes. So because temperature changes, so we have used different type of transistors. So these transistors which is used within the op-amps, the base emitter voltage will changes. So all these value will changes. So a circuit carefully multiplied by the 25 degree Celsius may not be remain constant. So when temperature it rises up to 30 degrees Celsius, though this is called drift. Often this current is called a drift current and expressed by in nano ampere per degree Celsius. And offset voltage is called a drift voltage, that is expressed into millivolt per degree Celsius. So these things indicates the change in offset for each degree Celsius and with respect to temperatures. So this all about the DC characteristics of the op-amps. Next we will discuss about the AC characteristics of op-amps. So in AC characters we will discuss about only two characteristics. First is a frequency response, second is a slew rate. For small signal sinusoidal applications for AC characteristics, so first is a frequency response, second is slew rate. So what is the frequency response? An ideal op-amp has infinite bandwidth. We have already discussed in case of ideal op-amp the bandwidth should be infinite. And that is a open loop gain should be approximately 90 dB with the DC, and this gain should be remain same through the audio and radio frequency. High range frequency it should be same because we have already assumed that its bandwidth is infinite. But in practical cases the gain should be decreased as frequency increases. Already we have discussed in a frequency response of the amplifiers. We can see if the initial frequency gain increases, at mid-band frequency ranges gain is a constant, at the high frequency ranges gain again start to decreasing of the amplifier. So this is called it low frequency range, this is called the mid frequency ranges, after this is called the high frequency range. So we can see here at the high frequency ranges the gain of amplifier is start to reduce. This is due to the capacitor component to equilibrium, because at a high frequency there are different type of capacitors exist in circuits. Sometimes the parasitic capacitors like CD and internal capacitance also existed. So these capacitors reduce the value of gain at the high frequency. So we can also write the using this formula gain equal to A is open loop gain into 1 divided by 1 plus f1 f divided f1 का whole square. So in this way we can decide the frequency response of the op-amps. Next we will discuss about the slew rate. Slew rate is a define the maximum rate change of output voltages caused by the step input voltages and usually specified by the microvolt per second. That means this we will see using draw this diagram. Suppose that this is the input voltage. Suppose so how much voltage, how the very fast how much voltage is changing using this for a step change in the input. So this is the called it. Suppose that this step changes like this. This is the called slew rate of this op-amp. So maximum rate change of the output voltages with respect to change in input offset voltages. So the rate change of output voltages due to step inputs voltages and usually specified volt per micro. For example, 1 volt or 1 microvolt seconds. This is the unit of the slew rate. So how will calculate the slew rate? This is the we can say DC. This is the change in output DC voltage, but change in input times is nothing but IC current by capacitor value. So the slew rate. So maximum slew rate in case of open 15 microvolt per seconds. One IC we can use designing this op-amp. That's IC name is a 741 IC. So we will discuss about this IC, how many pins in this IC, and what are the use of this pins and block diagram of this IC. The pin configuration of IC 741 is operational amplifier. We can draw here. It comprises the 8 pins where the function of each inputs we will discuss one by one. This it is a 741 is 8 pins IC. This is the seven number of pins 74. This is the 8 pins is there. First pins name is a offset null. Second is a inverting terminal. We are providing the input here, inverting terminal here, and third pins name is a non-inverting, and four pin name is a VCC, supply voltages. We supply VCC positive or VCC negative, and fifth pin is a offset null, and sixth pin is a output. We take the output at the sixth pin, and 7 page is a positive VCC supply, 5 is a negative VCC supply, and 4 is a negative VCC supply. Suppose that this are the op-amps. We can see this diagram easily, we can understood. Suppose that this is the V1 is here, V2 is here, and V1 is here, and this is the VCC supply. This is the VCC positive, and this is the VCC negative. VCC positive means this is 7 pins. Pin number 7. VCC negative is nothing but pin number 5s in this diagram. In 7 page not connected pins, this one extra pin is there. So the 741 IC is a high performance maintenance and monolithic operational amplifier. Some features we can say: the high common mode voltage ranges make the micro ampere 741 that can use the voltage flower. Second feature of this 741 IC is internally frequency compensation is there, means gain is increasing, so the frequency range, mid frequency range must be even the constant. Offset voltage null capacitance is also available. It consumes the low power. So this is all about the op-amps features. So next we will discuss about the mode of operation. How many mode of operation and possible non-inverting amplifier? First is open loop operation configurations. When connected in open loop mode, op-amp is simply function as a high pass, high gain amplifier. This is the op-amp. First, when we amplified the op-amp into non. So three type of configuration. This is suppose this is the op-amp. 3 type of configuration is possible. This is the negative terminal. This is the negative terminals. We will discuss one by this. For differential configuration. Differential configurations means, suppose that this is the differential configuration. This is the op-amp. In op-amp, this is the V1 and this is the V2. This negative and this negative. This is the called it differential mode. We are providing differences output. Second is a non-inverting mode. We suppose this is the op-amp is here, negative terminals output. This is feedback is here. We are providing input here, and output terminal must be grounded. This is the non. Second, we will discuss about the non-inverting terminal. Suppose this is the op-amp is here, positive, negative. VI input is here, op-amp feedback is here. So, in case of non-inverting, inverting terminal must be provided 0, and the input should be providing in the non-inverting terminals. So three configuration generally possible in the op-amps. 8 inverting amplifier. This is the most widely used of the all op-amp circuits. The output voltage V0 is feedback to the input terminals, means this diagram is shown here, non-inverting terminals, because in input we are providing a negative terminals. Here we have already discussed this. In positive terminal should be ground feedback resistance. So this most widely used is the op-amp circuit, output feedback inverting amplifier. So we can write its outputs RC equal to direct minus RF via Rin into Vin. This is direct output we can write here. R1 and RF network. RF is feedback amplifier. This is the feedback amplifier. This is the feedback resistance. Feedback resistance is here. This is the input resistance. This is the input resistance. This is the input voltages. Yeah, this is the input voltages. R1 connected through the inverting terminal. This terminal is called inverting. So direct output we can write here. So this is about the non-inverting terminal. Second, we will discuss about the non-inverting amplifier. This is the non-inverting amplifier. Means the input terminal here we can see input terminal is grounded and negative terminal is inverting terminal is grounded and input is providing the positive terminal or non-inverting terminal. This is the feedback resistance. This is the feedback resistance. This is the input resistance. We can see input resistance. So direct we can write the output here 1 plus RF by R1 into V into Vin. This is the called Vin. Here the signal applied to the positive terminals and feedback is given to circuit without inverting amplifiers. We can drive these output voltage using the KVL here. So this is not required, I think. Otherwise we can also drive here. We can use the KCL at this terminals. If using the KCL at this terminal, how we can? So 0 minus, suppose that this is the 0. So here must be 0 because of virtual ground condition. Virtual ground means these terminal must be same voltages, so that differential input should be 0. That's called the virtual ground. Because of virtual grounded, this terminal must be 0, and we can use the KVL here for driving this formula. So 0 minus V input, 0 minus V in via R in plus we have assumed the current flowing through the, and again 0 minus V0 divided by RF, or for in case of ideal op-amp when virtual ground is exist, so there is no current flow through the op-amp, so that's why inner current must be 0, and we can solve this and we can get the output voltage is equal to minus RF via R1 into Vin. So using similar way we can also drive the execution using the KVL, because here using the virtual ground condition, here voltage must be V input because we have assumed op-amp is ideal. So virtual both positive and negative terminals they have same voltages. Then again we can use the KCL here, V input minus R1 divided plus V input minus R divided by R2, and we can solve this equations, and we get output equal to 1 plus RF via R2 via R1 into Vin. Here RF nothing but R2. This is the RF and nothing, feedback resistance is R2. Second is a differential amplifier. So next class we will discuss about the differential amplifier. Today is the last topic we have discussed is a non-inverting amplifier.